2.1. This is Mr. Saari. Okay, so lesson 2.1, we have some learning targets. So after this lesson, you as the student will be able to define real, imaginary, and complex numbers. You'll be able to perform operations of all types with complex numbers. You'll be able to simplify and perform operations with square roots of negative numbers. And you'll be able to find complex solutions of quadratic equations by using the quadratic formula. All right, starting out. Definition of I. I is called an imaginary number. And the reason why it's called imaginary is because it comes from the square root of negative numbers. Negative numbers can't have square roots, which is why we call them imaginary. So a number times itself cannot be negative, which is why we came up with this number for I. So I represents imaginary numbers. I squared, by extension, would then have to be the square root of negative 1 squared. And if we square a square root, like the square root of 2 squared is just 2, because it's the square root of 4. Square root of 2 times square root of 2, which is square root of 4, which is 2. So square root of negative 1 times the square root of negative 1 is just negative 1. So I squared is negative 1. That's an important property that you need to be able to use when we're doing operations. So if we're simplifying the square root of negative 81, we can write square root of negative 81 as the square root of negative 1 times the square root of 81. That's why we can bring out the I, so to speak, and make it I times the square root of 81. And we know square root of 81 is 9, so this is equal to 9I. 9 times I. I times 9 are 9I. And complex numbers are always written in the form A plus BI. So notice how we have a real number component and an imaginary component. So you have the real plus the imaginary part of it is what makes this whole thing into what's called a complex number. So real numbers are just normal numbers, normal counting numbers, 1, 2, 3, 4, 5, 1.2, the square root of 3, anything that doesn't involve I. Imaginary numbers are numbers that are multiples of I, so some number times I essentially. And together, when you add them, you get what's called a complex number. Okay, so number operations with I. So when we are adding, subtracting, multiplying, and dividing, we essentially treat I just like it's an x or any other variable. You treat it just like any other variable. The one exception to that rule is that anytime that variable is squared, anytime I is squared in your final answer, you can actually simplify it into negative 1 and then simplify further. So, doing some examples. When we add two polynomials, we simply just combine like terms. So 7 and 1 make 8. 2i and negative 4i make negative 2i. And that's your final answer, 8 minus 2i. Next, we subtract. We're subtracting polynomials. You may recall that when you subtract a polynomial, the only difference is that you got to distribute this negative in. So that turns into plus 9 plus 11i. And this first binomial doesn't change, so we got negative 7 plus 5i, plus 9 plus 11i, and now we just combine like terms. Negative 7 and 9 combine to be 2, and then 5i and 11i combine to be 16i. Notice how I always write it in that complex number form, real number first, imaginary number second. So those are our two answers to those two problems. All right, multiplying. Multiplying, again, you're still just treating I just like any other variable. So we distribute 8i into 2i and into negative 7. So we have negative 8i times 2i is negative 16i squared. Negative 8 times 7 is plus 56i. And remember, the one difference was any I squared term ends up turning into negative 1 due to this property right here. I squared equals negative 1. So negative 16i squared is negative 16 times negative 1 plus 56i. That would be 16 plus 56i. And double checking to make sure we have it written in that standard form, real number first, imaginary number second, which we do. So that is our answer right there. All right, again, 5 minus 2i squared. treat I just like any other variable. And if this was 5 minus 2x squared, you would start by foiling this. So we do 5 minus 2i times 5 minus 2i. That's how we square a binomial term. And now we perform our distribution. 5 times 5 is 25. 5 times negative 2i is negative 10i. Then negative 2i times 5 is negative 10i again. Negative 2i times negative 2i is positive 4i squared. All right, so we combine like terms. So I've got 25 minus 20i plus 4i squared. And if you recall, the one difference with I compared to any other variable is that I squared turns into negative 1. So this turns into 25 minus 20i plus 4 times negative 1. And now we can continue this. This is actually negative 4. 25 minus 20i minus 4, or plus negative 4, same thing. And now I can combine like terms with my two constant terms. 21 minus 20i. Notice I took care to write the real number first, imaginary number second. Okay, so this is more of the same. Multiplication, you would distribute this. Okay, let's talk about division a little bit though. We got 3 divided by 4 plus I. 3 divided by 4 plus I. Whoops. How we perform that operation is you essentially you cannot have complex numbers in the denominator. You cannot have i's in the denominator, so we got to do something to get rid of them. And what we do is called multiplying by the conjugate. 4 minus I over 4 minus I. You might remember this as something that you would do. It's similar to, or almost exactly the same as, let's see, had this problem. 4 plus the square root, whoops. Whoa, what just happened there? 4 plus, let's say, the square root of 2. So just like we would need to rationalize the denominator here, we want to rationalize the denominator here as well. So we would, for this one, you would rationalize by multiplying by the conjugate, keeping the first number the same, reversing the sign of the second number, and then distributing. So you distribute, multiply it out, and you end up getting 12 minus 3 root 2 over 14, because the radical would end up canceling out, and you'd have 16 minus the square root of 4, which is 14. But so notice this is the same thing as this. We keep the first number the same, multiply by the opposite sign of the second number. So we distribute these out. Distributing in to both, 12 minus 3i over, so we've got 4 times 4, which is 16. Remember, we're distributing. 16 plus 4i minus 4i, and that was the point to get rid of the i's, and then minus I squared. So those cancel, the 4i and the negative 4i. And then I'm left with 16 minus negative 1 down here. Well, that turns into plus 1. So on the bottom, I've got 17, 16 plus 1. And then up top, I've got 12 minus 3i. And this is a perfectly acceptable final answer. So notice how I rationalized the denominator by getting rid of the I term. And I did that by multiplying by the conjugate on top and bottom. All right, last example, okay, this is again more of the same. You'd multiply by the conjugate, so I'm not going to work completely through this one, but you would multiply by 3 minus 2i over 3 minus 2i on top and bottom, making sure to distribute completely following those rules of distribution. All right, working with complex numbers. So simplifying, then combining like terms. So the first thing you have to do is get all this stuff in terms of I. So this is I root 64. Remember, this breaks down into the square root of negative 1 times the square root of 64. That's where we get I root 64 minus I root 25. Again, those can simplify. 8i minus 5i, which is simply just 3i. Again, just adding a step out front, then combining like terms. For this one, same thing. Simplify everything as much as you can first, then actually perform the operation. Negative 5 minus I root 9, but root 9 is 3, so I got negative 5 minus 3i. That whole thing squared, then you'll go through the song and dance of multiplying this out. So again, distributing, because that's what we always do when we got a binomial times itself. 25 plus 15i plus another 15i plus 9i squared. This turns into plus 9 times negative 1. Combining like terms to get 30i. So then that's negative 9. 25 plus 30i minus 9. Subtract 16 plus 30i. Final answer. All right, finally, solving using the quadratic formula. Remember, the quadratic formula is kind of like the last resort for solving a quadratic equation like this. Remember, we could solve by factoring. We could solve by completing the square. Solve using the square root method under certain conditions. Or we can solve by using the quadratic formula. Remember the quadratic formula, if you have ax squared plus bx plus c equals 0, the quadratic formula is this. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All over 2a. So this will lead you to the answers to this. Just like if I were able to factor this, that would also lead me to the answers. This doesn't factor though, so we can go ahead and start plugging things in. So x is equal to negative b. Remember, here a is 1, b is negative 2, and c is 17 for this particular problem. So I've got positive 2, because negative 2 is positive 2. So 2 plus or minus the square root of b squared, that's negative 2 squared, minus 4 times a times c, all over 2 times a. So this is 2 plus or minus the square root of 4 minus 4 times 17 is 68, all over 2. 2 plus or minus the square root of negative 64, all over 2. That happens to simplify to I root 64, which is 8i. 2 plus or minus 8i, all over 2. And remember, I can reduce this if they all reduce. So divide all these by 2. And I get 1 plus or minus 4i all over 1, which I can just drop the 1 and get x equals 1 plus or minus 4i. And there's my final answer. It's possible, though, that at times when you use the quadratic formula, you might get an answer that ends up being some number plus or minus I root some other number over some number. It doesn't always have to simplify into a nice rational complex number, or a complex number with rational coefficients. All right, that is our lesson for lesson 2.1.